Welcome to today's webinar. The topic today is RFEM 6 and IFC, presentation of relevant program features. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today, and I will answer your questions during the webinar. My colleague Lukas Sühnel will do the presentation. He's the main responsible person for the development of the interfaces in RFEM 6 and RStab 9, and he works also in the customer support team. You can ask questions when you press the button with the question mark, then enter your question in that field, press send, and I will receive your questions and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Lukas. Lukas, you can start.
Andreas, thank you very much for the introduction. I will continue with the content. What do I want to show you today? It is about the IFC workflow in RFEM 6. The integrated IFC viewer will be a topic. Afterwards, the conversion of those IFC objects into native data objects. Then we have the topic of the coupling. We have some new features for coupling these uncoupled objects, the nodal and line links. And the latest feature is then the rule-based link generator that I want to introduce. And at the end, I want to briefly show you the IFC export. Let's start directly with the IFC model that I want to use for today's presentation. I'm using the BIM Vision IFC viewer for that. And you can see it's some mixed structure. We have here a steel structure on the left-hand side and a regular simple concrete structure on the right-hand side with some columns inside and so on. Concerning the steel structure, there are already some steel joints included, some bolts, some stiffeners and so on. So this is the IFC file that I want to use for the creation of the analytical model in RFEM 6. How can we use such an IFC file? This can come from Revit, Tekla, or any other CAD program. How can we use it? Well, let me show you in RFEM 6 directly. First of all, we have to import the IFC file. I think this is clear. Via File, Import, IFC, I can, that's the right path. I can select the IFC model and import it. Now, the first screen that will show up is dealing with the insertion point and the mirroring of these structures. And usually you will have to mirror it in the CAD software. The Z-axis usually shows upwards. In RFEM 6, often downwards. So in my case here, I have to mirror the Z and the Y-axis. Then the import will be started, and in a couple seconds, we will see the IFC file. All right. So that is the IFC file that we just imported, that we also saw in the BIM Vision viewer. And we can also show it inside RFEM 6. So what we currently see, this is no native data. We do not have any members. We don't have any surfaces. The objects that we see here, these are IFC objects, graphical objects. And we can display them because we have an IFC viewer integrated, as we can see here. And if we click on an object, we can also see the properties. Similar to any other IFC viewer, we can see that this is an IPE 450. And concerning the materials, it's German, but it's a metal, it's a steel S235. Yeah, so we can display also the information from those IFC objects in RFEM 6. And on the left-hand side, we have an additional navigator, and this navigator allows us basically to hide specific objects, specific members maybe, or in general whole IFC entities. Yeah, for example, the fasteners here. Yeah, I mean, I don't need them here in RFEM 6 right now. They are of no use currently. Therefore, I can, for example, hide those fasteners and any other object that I'm currently not interested in. And yeah, something like that. So what is the next step? We have graphical objects, but we need native data. So it would be nice if we can convert IFC objects into members and surface and maybe solids. How can I do it? Well, this is quite easy. When you have only the objects visible that you want to convert, you can select them and call up the context menu with the right mouse button and say here, convert into members, into surfaces or solids. Before we do this, we have to take care of the conversion. As we can see here, one more time, the material is so-called a metal construction steel S235. This is, even though it contains already basically the necessary information for the steel, the whole name does not fit to the name of our material in our own library. So after the conversion of such a steel, we will not get a valid material. Same for the cross-section, or for some of the cross-sections. The names are not always according to our database. For example, here the name is HEA beam HEA 120. This is not according to our library. So we have to convert these strings, basically these text fragments, into our own cross-section and material names. How can we do this? Well, we have here under the cat BIM menu, the conversion tables, and they are divided into the material and cross-section conversion tables, and we will import the additional information from that IFC file into those tables. And these tables will be extended whenever you import another IFC file. Yeah. So it's not a one-time conversion table that you create here. You can use it again and again and again, the more you fill it. Since mine is a bit messy here right now, I would say let's start from scratch. I will delete all the materials and all the cross sections. Oh, this is really a lot. I just notice here. Let me do it a different way. I hope it works this way. I'm selecting the first and the second. Yes. Okay, now I have empty conversion tables and I can manually fill them. That's also possible. Yeah? Instead of the IFC import filling us the tables, we can also manually fill them, and we can do it with this little button on the right bottom here. Add new entry from IFC object. So now I'm in the material conversion table and I want to import here the external material name. So I'll select this icon. I go into my navigator and select here. This is the entity, or the entity where I want to pick the name from. And then it will import me the name metal steel S235. And I maybe have to do it again for, let's say, the walls and maybe also for the slabs. So this import is always connected to one specific IFC object. Yeah. So for the beams, for the columns, for the slabs, for the walls, these are usually sorted in different IFC objects, and this import has to be done for each object type. And if I have it here, I can match it. I can click on these 3 points. Well, let's start with the concrete, because this is already the table that we see here. So I will pick here a concrete C3037. Can make a copy, And concerning my steel, I change the filter, maybe search for an S235 according to the Eurocode. And then my material conversion is done. And concerning the cross-section conversion, same logic. I can import the name from my columns, for example, here from the object type property, and it will import not just the IAPE 450 name, it will import all the names that are written in the object type for the IFC column entity. Now I have also IFC beams, so I do it one more time. I click on a new row here, select my beams. Again, for beams, IFC beam objects, I want to read the name from the object type here. And then I have all the necessary cross sections imported. And now I can simply assign my cross sections from the library. Let me do it here. IPE 450, I think it was. Did I type it in? Yes. Okay. Takes a second for some reason. Okay. According to some Eurocode manufacturer or related manufacturer, then I can copy it, just rename it here, IPE 600, and then I do it one more time for the HE3, oh, I can't say, HEA 300. Okay. All right, copy it. And then just change the numbers. And for the round bar, I just type in R20. Here I know the description, and it's a R20 section. For rectangular sections, we don't have to do it. The program will automatically detect the right dimensions. So this was a little bit of work, but as I said, these tables will be saved. So next time you run an import, these cross sections will be covered, and you can basically use it again and again. All right, now conversion is done. No, the material and section conversion tables are ready. We can do the conversion now of the beams. So let's hide some additional IFC objects to select all member-like objects in one step. Right mouse button and convert into straight members. Conversion is running on the bottom left side. You can see that, and it's done. And now let's do it also for the slabs and walls. And even though there are some RFEM members in the background, it doesn't matter. We can right mouse button here, select the IFC model objects, and say here one more time, convert into surfaces. All right. So now these objects that we see now are native RFEM objects. We have here members and we have surfaces. And we can also double check if the location is correct. How can we do it? For example, by switching the model data on and off. I have now, wait, where's my IFC? I deactivated the object types here. So this is my IFC, as you can see. And if I show my model, you can see it's basically on the same location. Yeah, it's identical to the IFC. All right, so that's good. We used the information from the IFC to get the right cross sections, the right materials into RFEM 6. Also, the thicknesses of the slabs and walls was taken from the IFC. So that is quite nice. What is not so nice, but it is, I think, common or well-known topic, the elements are not connected here. Yeah. Why is that the case? I think it's quite clear. Anyhow, let me briefly explain it one more time. with the conversion into members, we create the center lines in these objects, and these center lines have a start and end point, of course, and the start and end point is based on the start and end point of that IFC object. Since this beam is connected to the flange of the column and not the center line, and the center line of the column is in the center, as you know, there will be a gap. Let me show it one more time here on this specific example with the wireframe model. I think it's clear where the gap is coming from. So what can we do about it? We were always able to use functions in RFEM 6 to elongate, for example, members. I was always able to say, select a couple of members and say here, for example, extend and trim these members, extend them to the next member in line in both directions, and then those coupling members will be connected to the columns. This is working fine for this scenario here, for this single case. It is not working in such a way for these coupling members in the roof plane, simply because they are eccentric. They are not in the same level as the main beam. So a simple elongation extension will not solve it. I would have to project all these members into the plane of this beam, and then I can extend them. So it's quite a lot of work to connect this whole model together. So what else would be an option? Another option could be that we create couplings between these nodes and members and members and members and so on. And this is what we used as an idea for the next features that I want to show you. We recently implemented 2 new objects. And you can find them in the types for nodes and types for lines. And we call them nodal link and line link. And a nodal link is basically a little generator that creates rigid members. So if I can show it in a second. So what does this nodal link do? It will create a rigid link from a node that I have to select, and it will search for other nodes or other members or surfaces in a defined search area, search radius. So as an example, I can select a node, or let's do it for one first. I can select, for example, this node here from the main beam. Okay, and say, please connect to the next member within a 1 meter radius. I say okay, and it will connect to my column, which is good. This is what I want. And what will it do? As I said, it will create a rigid member. Okay, so what could we do now? We can do following. We can go into this nodal link and say, hey, instead of just starting from one node, let's select all the nodes. Let's just select all the nodes. Maybe also these down here. This one's. Say okay. And please search for another member close to your location, and let's see what happens. We can see that a lot of those nodes, more or less all of them, will be connected to a member close by. And it's looking actually not that bad. I mean, I'm showing the center, this wireframe model because it's more visible, but for the general orientation, all these coupling members, all these members in the roof plane are now connected to the columns and to the beams and so on. So this is looking quite nice. It's not that bad for spending, I don't know, not even half a minute for that. Let's have a further look here at the diagonals. And here we see, well, that's maybe not the expected result. I have here the diagonal members. They are not connecting to this node on the column. They are connecting to these coupling members, and this is actually not what I want to have here for my analytical model. The same for the diagonals down here and for other joints as well. So that's one little concern where we maybe have to do something against. The other thing is this one node link creates rigid members. And these rigid members, according to what I defined here, have no hinge. So every object is connected rigidly to the other object. So we have a completely rigid steel structure now, which is not correct for the latest structural analysis. Yeah. So what can we do against it? Well, we could create multiple nodal links and spend a little bit more time on selecting the nodes properly. So let me remove this one here. And let's think what we want to connect first. So let's say we have we have here different cross sections in the structure. And one is, for example, the IPE 600s. These are the main beams of my structure, and they have to be connected to my columns. So one node link could be to connect, or could deal with the connection of my main beams, these nodes, to my columns, so members close by. So this node link should look for members. And it should be a rigid connection, so I'm not defining any hinge. And this is done now here. Yeah, we can see all these couplings between the main beams and the columns are done. And if we want to be really nice, we can even rename this nodal link and call it, I don't know, column beam link or something like that. Then we can create another coupling. What could be the next one? Let's have a look. We have additional columns down here. I think the IPE 450. Yeah, so these center columns here, they have to be connected to the main beams, and also these columns on the outer frames should be the HEA 300. Also, those have to be connected to the main beams. Yeah. So another nodal link could be, let's call it inner column beam. And again, we are looking for connections from specific nodes, which I can select now, to members close by. Maybe we want to connect them not rigidly, but maybe hinged. So we can create a member hinge and connect them. So now they're also connected. And in this way, we can continue. And I want to do it so you can see maybe some obstacles that we will also face in here. And the next one will already show one of these little obstacles. So let's say we want to connect all the coupling members, yeah, from my structure, which is between my frames usually. They should be connected to the columns and so on, and to the main beam. So another node link. I skip the renaming now. I think it's clear how it's working. So I select all of those nodes. And again, I say, please look for members close by. And maybe use a hinged connection, yeah. Okay, now all those members have been linked to columns and so on, like I wanted, apart from these situations here, where I have the diagonals, yeah. From that node, it should look for another member close by. And it's not the column. The member that is even closer to this node is this diagonal. So it's connecting this way. It's logical, but it's not what I want to have here. So what can I do about it? I can go into this nodal link. Oh, actually not. Yeah, I can go into this nodal link and say, please exclude certain objects from this search. Please do not connect to my bracing members. Yeah. Exclude the bracing members from my search. And what will happen is this coupling member will now be connected to my column as I expected, and not to my diagonal beams here. So that's good. Let's continue. I think there's only one rule remaining for the diagonals. And what do I want to achieve? I want my diagonals to be connected to this specific node here. Yeah. Should be connected to the columns, not to my coupling members. So what will I do? I create another node link, and I say, this time, the selected nodes, let's select them quickly. Yeah. These selected nodes, the end nodes of my diagonals, from those nodes, please look for another node. Connect to another node, ideally the one on the column. So I press OK. And what will happen? Yeah, I mean, expected. It will not connect to the center node of my, or to this node on my column. It will connect to the end nodes of my coupling members. Yeah. So one more time, I have to go into my rule and say, hey, please exclude the coupling members, the nodes from my coupling members from your search. And now the diagonals are no longer allowed to connect to those nodes. Yeah, I excluded them. So the next node in a radius of 1 meter is the node on the column. So that's why they will connect to this one. And now my steel structure is connected properly, yeah, as I would expect it. Okay, so far so good. Now, what can we do about the concrete building? If we have a closer look at this one, we can also see the walls and the slabs are not connected. Yeah. Again, because of the same reason, the wall will end on the top and the bottom side of the slab, so there will be a gap. How can we close this gap? Well, we not only have the node links, we also have the line links in RFEM 6. And they work in a similar way. From the lines that you select, it will create a rigid coupling to other lines or surfaces close by. So same logic. Let's create one for the wall slab coupling. Yeah. What do I have to do in that case? Well, if I want to couple my walls with my slab, I have to select all the lines, basically the bottom lines of my walls and the top lines of my walls and so on. Yeah, this is what I have to do here. Okay. It should look for surfaces close by and connect to those surfaces. This is what is happening here right now. It will create rigid links. Yeah, that's how they are called. I named them incorrectly before. So this line link will create rigid links, and these links will connect the walls with the slab. Yeah. So I would have to do the same again for my walls. Yeah, I would have to select all the vertical lines for my walls so that they are connecting again with another slab, with another surface, which is a little bit of work. And I don't want to do it now because I think the logic is clear. Yeah. These are the nodal and the line links that we recently implemented. And they will help you to generate a connected analytical model that you can later on analyze, design, and so on. Now, the difficult part, or the part that currently we have to spend a lot of time on, is the selection of the nodes and the lines for these line and nodal links. This is a bit work intense. It's quicker than anything we were able to do before, yeah, but it's still a bit work intense. So what our idea was that we want to create a little generator that does this for you, that will select the objects. And you can find this little generator in the model data, on the base data, in the settings and options. And here we have the rule-based link generator. And you can create a new rule set here, or you can also do it here in the data navigator of RFEM 6. It doesn't matter. The activation of the rule-based link generator has to be done here in the base data. So before we do this, we want to get rid of what we just created here manually. So I get rid of all these rules. And if I delete them, the nodal links and the line links, all these little rigid members and rigid links will be removed. Yeah. So you're back to the completely unconnected model. So what can I do? I can call up my rule-based link generator. And here I can define types. And those types will connect certain objects with other objects. For example, really simple, the wall type. The wall type will select all the vertical lines of surfaces. And from those vertical lines, it will create a line link. And inside that line link is defined, please look for other surfaces. So when you select the vertical lines and you say, please search for other surfaces, it will connect to other walls. So this is the wall link. We have also a wall slab link. I think it's clear what this one is doing. It's selecting the horizontal lines of surfaces and connects them and let them search for other surfaces. So basically the slabs. And let's select one more rule. For example, the column slab rule, which would connect the end nodes of vertical beams. Vertical beams are usually columns. This one is selecting the end nodes. And in these end nodes, it will search for slabs, so for other surfaces close by. So these types here, if I define them here, they are creating nodal links and line links with specific informations. So let's press OK. Let's see what happens. Well, currently we can see nothing happened. Everything is still unconnected. And this is clear because I just explained it before. If we want to activate this generator, we have to do it here in the base data. So I can put here, I can select the rule set one that I just defined. And now all those couplings will be generated. Yeah, we can see it in the data navigator. It created now line links and also nodal links. And the two line links are for the connection of the walls with the slab and for the walls with the other walls. So all the manual selection that I had to do beforehand, with the lines and so on, I can skip it. It's no longer necessary. This is what this rule-based link generator is doing. And it also connected us these columns with slabs, basically. So I'm done for the whole concrete model on the right-hand side. The only thing I have to do is I have to define additional rules for my steel structure on the left-hand side, because this one is still unconnected, as we can see. And also for that, I have specific types. Let's have a look. I have, for example, here a beam member type. What is a beam member type? Beam means it will select the end nodes of members, of horizontal members, and connect them with other members, beam member, with other members close by. This is a rule that I need to, because I want to couple the coupling members with my columns, for example. I also want to have a coupling between my diagonals and my nodes, As we defined it beforehand, the diagonals should be connected to specific nodes. And last but not least, I want to have my columns connected to my members, to my beams, So this rule will select the end nodes, of vertical members, and search for other members. Yeah, this is the rule that I want to use to couple my columns with my main beams. Okay, I hope I didn't forget anything. Let's have a look what it will do. I press OK, and the rule will directly be used. We can see here the coupling members will be connected to my columns. Also here in the roof plane, we can see the coupling members are connected to my main beam. So this is all looking quite nice. We have a little issue here. My coupling member is not connected to my column. Instead, it will connect to the diagonal member. We had the same issue beforehand. So we have to go into this rule-based link generator, select here the beam member rule, and inside that beam member rule, I have to say, please do not use the diagonal members for the connection. The same we did before, yeah? Please do not connect to the diagonals. Press OK. And now, we can see it here, the coupling member is connected to the column. Now, the other issue that we have is, again, the same issue. The diagonals will not be connected to this node. They connect to this node. So these kind of definitions, these detailed settings, they have to be done in the rule-based link generator, similar to what we did manually before. Yeah. Exclude nodes from search. And here I select now all the nodes from my coupling members. And now the diagonals are connected properly as I would have imagined it. So these kind of settings have to be done in the rule-based link generator as well. But the selection of the nodes from where we want to have a coupling, this is done automatically. And we're still not finished. As you can see here, the columns are not connected to the beams. There are also these inner columns are not connected to my main beams, which is a little bit strange because, as you remember, we defined here this rule column member. So why is it not working? Well, we already have a column slab rule. And this rule here in the beginning or at the top, this one will be executed first because it has a lower object number. So this rule, what does it do? It searches for the end nodes of vertical beams of columns. Yeah, it searches for all the end nodes, and then it will try to connect these end nodes with a slab close by. This rule will be used for all vertical members, for all columns, so also for the steel columns. But this is not correct. Yeah, it should only be applied to those columns on the right-hand side. Because what is the issue? This rule basically uses all these nodes, yeah, and then those nodes are no longer existing for the second column rule, where I'm looking for other members. So what can I do? I can go into the column slab rule and say here, please apply this rule only, let's say, yeah, on this kind of structure here. Yeah, it should not be applied on my steel structure. And by doing so, the nodes from my steel columns are no longer utilized by the column slab rule, so they are free again, and then the column member rule will use them to connect them to the beams, which is what I expect. So now it's looking better. They are connected. The only little issue that we have here is that the columns are now also connected one more time to the main beam. This is not okay. Yeah, I don't want the connection from this column to this beam. So here I can go back into my rule-based link generator, and in this column member rule, I have to change the search radius a bit, that it no longer connects this node with the beam. Now I have a properly connected analytical model for the steel structure and for my concrete structure. And all I have to do now is define some supports. Let's do this quickly. Oh, that's the wrong. HEA 300 and IPE 450. Here we have a nodal support. And then we also want to support the concrete structure. The foundation slab, basically. And yeah, now the structure is supported and we can run the static analysis. I hope I made no mistake. This is just a little hint that we have lines which are equal, which is fine. They are the result of the line links of the coupling between the walls and the slab. Yeah, we have a wall on top of the slab and we have a wall on the below the slab. And from both walls, we are connecting to the slab. We are creating generated lines on the slab and they are identical. So that's why we have here this little warning about lines lying on top of each other, but it doesn't matter. So now we have the results. What can we see here? Well, let's change a bit to the wireframe mode. We can see the deformations. Maybe something I forgot to define here are some hinges for the bracing members. That's one thing I can optimize. But apart from that, I have here my internal forces, axial forces, bending moments, and so on. And if you compare it to a model that you build up in the, let's say, common way, you will see that they are quite identical. So the static analysis can easily be done with this model that we now connected with the rule-based link generator. Now we can continue with applying loads, running a steel design for buckling, lateral torsional buckling, and so on. I have to say there are some exceptions which we are aware of, which we will work on. And this is, for example, if we want to run the steel joint analysis right now. Due to the fact that we are using rigid members here, we currently can't use our steel joint add-on. It simply does not acknowledge these rigid members. But we already have a plan how we want to treat this so that you can continue working in your common way, in the common logic of RFEM 6, that also such joints can be designed in the steel joints add-on. Similar to the punching design for concrete, currently it's not the, how should I show it? The columns are not directly connected to the slab, so we are not aware of the cross-section from the column. Now it's this little rigid member. So again, there are some optimizations necessary in our design add-ons that we can keep working with them in the way that we know, that we are used to. But as a first step for using IFC files, I think this is the right direction. The rule-based link generator for, let's say, a more automated connection, or maybe the nodal links and the line links manually for a little bit more manual modeling. They can be used to connect these otherwise unconnected converted IFC file objects. So far regarding those two features, what else can I show you here? These generated objects, the objects that we generate from the rule-based link generator, or also these objects that we create from the nodal links and line links, we can always convert them into, let's say, ungenerated objects. So right now I have used my rule-based link generator to create nodal links and line links. Yeah. These objects are now generated. I can't modify them because, well, as I said, they are generated. You can, however, do it. You can unconnect them. You can cancel the generated state, and then they are open for your manual modification. So the same for the rigid members that we create with the nodal links. You can always cancel this generated state, and then this rigid member can manually be modified again. So even though maybe the final result of this generation is not 100% according to your expectation, you can maybe use it to generate the objects and then use them for further modeling by canceling the generated state. That's what I wanted to mention. The other thing that I want to show is, and now we are slightly switching to the latest chapter, to the export of the IFC model, is the saving of the originally imported information from IFC objects. So what did we do? We imported an IFC model. So I can show it one more time. I'm hiding my member, my RFEM model. And we can see here, this is one of these IFC objects that we imported. We have here the global ID 0TLI7 and so on. The global ID is quite an important information, in my opinion, because when we later on want to compare IFC models, this is usually what has been used to identify objects. It's a unique ID. This unique ID will also be saved inside our members. So now I'm here in the native RFEM data. And if I double click on this member, we have here this BIM tab. And in here, we see all the information from the IFC file. For example, also the global ID. 0TLI7, what I just mentioned beforehand. And when we now run an IFC export, this information will again be used in the now IFC object that will be created from RFEM. So let's do it. One more. Let's do it here. File, export, IFC. I'm mirroring this one again. Put it on my desktop. Export to. I can select here reference or structure analysis view. So in the old software generation, we always had only a structural analysis view export. With RFEM 6, you can also import into the IFC4 reference view. And this is an IFC file that other IFC viewers, CAD programs usually can open. So the export should be done. Let me quickly open this file. IFC export, no, export 2.ifc. So here we are. This is the IFC file that was just created by me with the Dlubal Software. And we can again see these elements. We get the information from the cross section, and in here is also mentioned the material according to RFEM 6 now, S235 35 and the material standard. And if we click on the same column again, this is this one here, we can also see it has the same GeoID. So this IFC file that we exported from RFEM 6 can now actually be used for a comparison with the original IFC file. Maybe to track the changes, track if we used a different cross-section or material, or if we moved the object around, because the GeoID is the same. And with this new logic of coupling elements, you can also see these IFC files look nicer. The beam stops at the location of the column, and it's not intersecting the column into the center line. What usually would happen if you do your regular modeling of analytical files. Yeah. So this is also, let's say, a little bit of a benefit of this new way to model your analytical models. Yeah. And with that being said, I am at the end of my part. I hope I was able to show you some new features, the nodal links, the line links, and the rule-based link generator. I hope that they help you in maybe further use cases where you want to work with IFC files. And if you have any feedback, please let us know. Yeah. And again, with that being said, I hand it back to you, Andreas.
Thank you, Lukas, for your presentation. At the end of the webinar, I have an additional hint for you to our online courses. There's the RFEM 6 course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with RFEM 6. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. And the Eurocode 8 course for the earthquake design. For more information and prices, just scan the QR codes or click at the links. You can get such a course for free when you submit your custom project and when we will publish it. Just scan the QR code or click at the link, and there's a form where you can upload all the files. And as promised, you will get a course with a value up to 399 euros when we have published it. Then there are free online services, for example, the Dlubal community. You can ask questions there, and our employees or our community members will answer you. Then there's the GeoZone tool for the determination of snow, wind, and earthquake loads. Then you can determine cross-section properties. You can download 3D models, for example, as a template for your project. You can also download our free trial versions of RFEM 6, RSTARP 9, RWind 3, or R-Section. Just scan the QR code here. You can find our free services when you click at the links or scan the QR code. You can get more information on our website. You can, for example, find the recorded webinars there. Then the knowledge base articles, for example. You can ask our AI assistant Mia 24/7, all the time. Just try it. Okay, that should be also all from my side. I thank you for your attention. Thank you, Lukas, for your presentation. I hope we meet each other in a future webinar. See you then. Bye-bye.